Allora, buongiorno a tutte, buongiorno a tutti, benvenuti al webinar organizzato da dal titolo AI Revolution, Exploring How AI Can Boost Your Business. Io sono Erika Bruno, Marketing Specialist di Into e oggi con me ci sono Rasha Jabbur, AI Engineer e Paolo Ferrante, Business Development. Vi do giusto alcune informazioni tecniche prima di iniziare, poi vi lascio al webinar. Vi chiedo di seguire con microfono e webcam spenta per evitare di sovraccaricare la connessione e permettere a tutti di seguire correttamente. Il webinar verrà tenuto in lingua inglese, ma appunto ci siamo sia io che Paolo che possiamo provvedere a tradurre eventuali traduzioni in lingua italiana o in lingua inglese. Vi chiedo di, nel caso abbiate necessità, di attivare i sottotitoli generati automaticamente nel menu che trovate qui in basso. Per qualsiasi domanda sui contenuti del webinar potete appunto scriverla in chat, sia in lingua italiana che in lingua inglese, e ci penseremo noi appunto nel caso a tradurre le domande. Detto questo, buon webinar e lascio la parola a Rasha. Rasha, I give you the floor.
Thank you, Erica. Hi, everyone. My name is Rasha Jabbour, and I am an AI engineer at Hinto Group. My specialties include data exploration and processing, as well as machine learning model building. At Hinto, we specialize in digital product development, AI solutions, and user experience and user interface design. Today, we will be exploring the different aspects of how AI can boost your business and how to best utilize its potential. So let's start up with how AI solutions have already taken place in the marketplace. So according to a survey carried out by HPE and Industries of Things World on 858 professionals and executives on European industrial companies, the majority of those interviewed, which are around 61%, are already involved in some capacity in AI. 11% have already implemented technology in basic functions or activities. 14% plan to do so in the next 12 months, and 36% are evaluating its implementation. If 2023 is considered the year of discovery, then according to some market studies, 2024 will be the year of consolidation and maturity for AI. Taking into consideration the Italian market, according to the report released by Anitech Assinform, in 2022, the AI market in Italy reached a volume of 435 million euros. This boosted up to 520 million euros by 2023, and it is forecasted to reach 1,200 million euros by 2026. Now, let's go over some of the most famous types of AI solutions we can find nowadays. First of all, predictive maintenance. Predictive maintenance involves using AI algorithms and data analytics to predict when equipment or machinery is likely to fail. These algorithms analyze historical data, sensor readings, and other relevant factors to forecast potential issues. By predicting failures before they occur, businesses can schedule maintenance proactively, reducing unplanned downtime and preventing costly breakdowns. Predictive maintenance helps optimize resources by ensuring maintenance activities are performed only when necessary, rather than on a fixed schedule, saving time and money. It also allows for better planning and resource allocation, as well as maintenance teams can prioritize tasks based on the urgency and severity of predicted failures. Next, let's talk about AI assistants. AI-powered virtual assistants are designed to simulate human conversation through natural language processing techniques. They can be integrated into various platforms such as websites, messaging apps, and customer service portals to provide instant assistance to users. These assistants can handle a wide range of tasks, including answering frequently asked questions, providing product recommendations, processing orders, and resolving customer issues. They offer round-the-clock support enhancing customer service efficiency and satisfaction by providing instant responses and reducing wait times. They can also collect data on the user interactions, preferences, and behavior, which businesses can use to improve their products and service and tailor their marketing strategies. AI systems have also been increasingly used in medical diagnostics to analyze complex data from medical images, patient records, and clinical tests. These systems can detect patterns, anomalies, subtle changes that may be indicative of diseases or conditions, aiding healthcare professionals in accurate diagnosis. AI-enabled diagnostic tools can analyze large data sets quickly and efficiently, helping to identify diseases at an early stage when treatment is the most effective. They can assist in risk assessment, prognosis production, and treatment planning, leading to more personalized and targeted healthcare interventions. AI in medical diagnostics has the potential to improve patient outcomes by reducing diagnostic errors, enabling timely interventions, and supporting evidence based decision making by healthcare providers. Now, we can categorize the types of AI into three categories. First of all, reactive AI. Reactive AI is often employed in systems like automating trading algorithms in finance, and it operates purely on inputs and predefined rules without actively learning from past experiences. These algorithms optimize outputs by swiftly processing incoming data and executing trades accordingly. For instance, in the realm of finance, automated trading systems react to market fluctuations and execute trades based on predetermined conditions without the need to learn or adapt from previous market behaviors. Then we have limited memory AI. This can be seen in autonomous vehicles, for example, and they possess the capability to adapt and improve based on past experiences or new data. These systems learn from previous driving encounters to enhance performance and ensure safety on the road. For example, autonomous vehicles use past data on road conditions, traffic patterns, and user interactions to refine their driving behaviors, making them more adept at navigating complex environments over time. Finally, we have theory of mind AI. This represents the pinnacle of artificial intelligence sophistication, characterized by its extensive ability to learn, retain, and apply past experiences in interactions akin to human cognition. Advanced chatbots deployed in customer service settings exemplify the level of AI, as they are capable of understanding nuanced customer queries and providing personalized assistance by drawing on a vast reservoir of past interactions. By leveraging a comprehensive understanding of human behavior and language nuances, theory of mind AI enables a more empathetic and tailored interactions, enhancing the overall user experience. Now let's talk a little bit about chatbots. In the evolution of AI assistants, there has been a notable shift from traditional chatbots to more advanced AI assistants, driven by significant advancements in machine learning and natural language processing technologies. Previously, chatbots were primarily rule-based or scripted, meaning they followed predefined rules and responses. These rule-based chatbots often lack the ability to understand complex queries or adapt to user behavior beyond the scope of their programmed rules. While they served basic functions in applications like customer service and virtual assistants, their capabilities were limited by their fixed responses. In contrast, modern AI assistants leverage machine learning algorithms to continuously improve and adapt based on interactions with users. These machine learning based chatbots, also known as conversational agents or AI assistants, are capable of learning from vast datasets of user interactions to enhance their understanding and response accuracy. They employ sophisticated natural language understanding models to decipher nuanced queries and provide more contextually relevant responses. One key difference between traditional chatbots and modern AI assistants lies in their ability to learn and evolve. While rule-based chatbots operate within the confines of predefined rules, machine learning-based AI assistants dynamically adjust their responses based on the context of the conversation and feedback from users. This adaptive learning capability enables AI assistants to provide more personalized and human-like interactions, significantly improving the user experience across various applications such as customer support, virtual assistants, and conversational commerce. Furthermore, modern AI assistants often integrate with other systems services, allowing them to perform a wider range of tasks beyond simple conversation. They can access and manipulate that data from various sources, execute commands, and even automate tasks, making them powerful tools for enhancing productivity and efficiency in diverse domains. Overall, the transitions between rule-based chatbots to machine learning-based as AI assistants represents a significant advancement in the field of artificial intelligence, offering more intelligent and adaptable solutions for human-computer interactions. Examples would include virtual assistants like Amazon's Alexa, customer service chatbots on websites, and social media chatbots for marketing and engagement. Now, we've mentioned the word natural language processing quite a bit. What is natural language processing? NLP is a branch of artificial intelligence focused on the interaction between computers and human language. It enables computers to understand, interpret, and generate human language in a way that is both meaningful and contextually relevant. Natural language processing has three key components: natural language understanding, natural language generation, and natural language processing models. These three are interconnected fields within the broad domain of artificial intelligence and computational linguistics. They deal with the interaction between computers and humans, natural languages. NLU focuses on enabling computers to understand and interpret human language in a way that is both meaningful and useful. It involves tasks such as syntax parsing, which analyzes grammatical syntaxes of sentences, semantic analysis, which would extract the meaning of words, phrases, and sentences, sentiment analysis, which would determine the sentiment or opinion expressed in a piece of text. NLU systems often utilize techniques such as machine learning, deep learning, and rule-based approaches to achieve accurate understanding of natural language inputs. Natural language generation, on the other hand, involves the generation of human-like language by computers. It aims to produce coherent and contextually appropriate text based on underlying data or instructions. NLG tasks would include text summarization, machine translation, and generating product descriptions for e-commerce websites based on specifications. NLG systems can employ techniques such as template-based generation, rule-based generation, and more advanced methods like deep learning-based generation using recurrent neural networks or transformer models. Finally, we have natural language processing models. These models encompass a broad array of algorithms and architectures designed to facilitate the understanding, generation, and manipulation of human language by computers. These models have evolved significantly over time, driven by advancement in machine learning, deep learning, and computational linguistics. Examples would include transformers architectures, including BERT, GPT, and their variants used for tasks like language translation, text summarization, and question answering. Now, the NLP can be applied in various stages. It can be used for virtual assistants such as Siri, Google Assistant, and Amazon Alexa. These assistants understand voice commands, respond to queries, and perform tasks like setting reminders or searching the web. Then there's language translation like Google Translate or DeepL. These translate texts from one language to another with high accuracy, enabling communication across linguistic barriers. Then there's text analysis and summarization. like summarizing lengthy documents or news articles. These algorithms can extract key informations and generate concise summaries, aiding in quick understanding. And finally, we have sentiment analysis, which is basically analyzing social media posts, for example, to gauge the public opinion about products or brands. This helps businesses understand customer feedback and sentiments towards their products or services. Next, let's talk about large language models. Large language models are considered a branch of NLP. They are advanced AI systems designed to understand and generate human-like text at an unprecedented scale. They leverage deep learning techniques and massive amounts of data to achieve remarkable language comprehension and generation capabilities. LLMs are trained on a vast data set comprising billions or even trillions of words, allowing them to capture intricate language patterns and nuances. For example, OpenAI's GPT-3 model, also known as ChatGPT, was trained on 175 billion parameters, demonstrating exceptional text generation abilities across diverse topics. LLMs also utilize self-attention mechanism to weigh the significance of different words in a sentence, enabling them to understand context and relationship effectively. For example, transformer architectures, which is a key component of LLMs, facilitate parallel processing of input tokens, enhancing efficiency in understanding and generating text. LLMs can also be fine-tuned on specific tasks or domains by providing additional training data or adjusting model parameters, making them adaptable to various applications. For example, like fine-tuning GPT-3 for tasks such as text summarization, language translation, or code generation, or even many more tasks, which would improve performance in specialized areas. LLM can be applied in content generation. LLMs like GPT-3 can produce coherent and contextually relevant text across diverse genres and styles. For example, generating articles, stories, or even poems based on prompts or input provided by users. They can be used as conversational agents since they power conversational interfaces capable of engaging in natural language dialogues, answering questions, and providing assistance to users. For example, chatbots, virtual assistants, and customer service agents. And they can also be used in code generation as they can assist developers by translating high level instructions into executable code, speeding up the development process. For example, automatically generating code snippets or completing programming tasks based on natural language descriptions. Next, let's talk about the most talked about branch of AI nowadays, which is Gen AI, also known as generative artificial intelligence. Gen AI is a branch of AI focused on creating machines that can generate new content such as images, text, or music that closely resembles human created content. Gen AI algorithms learn from existing data to produce novel outputs, enabling applications in creative fields, content generation, and beyond. Algorithms capable of generating new data that is similar to but not identical to the training data is a key component of Gen AI. For example, generative adversarial networks, or for example, the autoregressive models like OpenAI's GPT series. Another key component is the high quality and diverse datasets used to train Gen AI models, providing examples of the content to be generated. For example, a dataset containing thousands of images of cats can be used to train a Gen AI model to generate new realistic images of cats. Gen AI can be applied to content generation as they power applications for generating text, images, and videos useful in content creation and marketing. Like OpenAI's DALL-E model generates images from textual descriptions, enabling users to create visual content based on written prompts. They can also be used to create digital art, generate music, and produce other forms of creative content. For example, Midjourney is a prominent Gen AI tool for crafting images from text inputs. And they can also be employed to generate synthetic data for training machine learning models, improving performances and generalization. Like NVIDIA's StyleGen can create realistic synthetic images, augmenting datasets for training computer vision algorithms like image classifiers or object detectors. Now that we saw how AI has already and will continue to impact the industry, let's move on to how these AI models are built. One popular framework would be TensorFlow. TensorFlow is an open source machine learning framework developed by Google, designed to facilitate the creation, training, and deployment of deep learning models. It provides a comprehensive ecosystem of tools, libraries, and resources that enable developers and researchers to build and experiment with various neural network architectures for tasks like image classification, neural language processing, and more. Some key features would include flexibility, as TensorFlow supports a wide range of machine learning tasks, including classification, regression, clustering, and deep learning. It also allows seamless scaling from prototyping on a single machine to training and deployment across distributed systems. It is optimized for high performance with supports for GPU and TPU acceleration, enabling faster training and inference times. It supports various platforms, including desktop, mobile, web, and cloud, making it suitable for a diverse range of applications. TensorFlow can be applied in many aspects of the industry. For example, in the case of healthcare, TensorFlow is used for medical image analysis, disease diagnosis, drug discovery, and personalized medicine. For example, it powers AI-driven diagnostic tools for identifying anomalies in MRI scan and detecting cancerous cells in pathology slides. It can also be employed for fraud detection, risk assessment, algorithmic trading, and customer segmentation, which makes it a useful tool in finance. Financial institutions leverage TensorFlow to analyze large volumes of data and identify suspicious activities in real time. TensorFlow is also utilized for manufacturing, for predictive maintenance, quality control, supply chain optimization, and robotics. It enables manufacturers to predict equipment failures and optimize production processes, as well as enhance product quality through defect detection. TensorFlow is also popular in retail as it powers recommendation systems, demand forecasting, customer sentiment analysis, and inventory management. Retailers leverage TensorFlow to personalize product recommendation, forecast sales trends, and optimize inventory levels to meet customer demands. Now, artificial intelligence, machine learning, and deep learning are often used interchangeably, but they represent different aspects within the realm of computer science. AI refers to the broader field of creating computer systems that can perform tasks that typically require human intelligence. Machine learning is a subset of AI that focuses on enabling computers to learn from data without being explicitly programmed. For example, consider a spam email filter. Traditional programming would involve creating rules to identify spam, while in machine learning, the filter learns from examples of spam and non spam emails to prove its accuracy over time. Deep learning is a subset of machine learning that employs artificial neural networks with multiple layers to process data hierarchically. A common example of deep learning is image recognition, where a neural network learns to identify objects in images by analyzing patterns in the pixel data. In essence, while AI encompasses the broader goal of mimicking human intelligence, machine learning and deep learning are specific approaches to achieve this goal through learning from data. Like I just said, machine learning is a subset of AI that focuses on the development of algorithms and models that enables computers to learn and make predictions or decisions based on data without being explicitly programmed to do so. The goal of machine learning is to enable computers to learn from experience, this experience being data in this case, and improve their performance on a given task over time. Various machine learning models and algorithms are employed across industries to solve diverse business problems and optimize processes. We will focus on two types of machine learning: supervised and unsupervised learning. In supervised learning, the model is trained on labeled data where input-output pairs are provided. Some common algorithms include logistic regressions, which is employed for binary classification tasks such as spam detection or customer churn prediction. Support vector machines, which is effective for classifications and regression tasks with complex decision boundaries such as image classifications or handwriting recognition. And decision trees, which is used for classifications and regression tasks, providing interpretable decision rules such as credit risk, assessment, or medical diagnosis. Now, what does it mean when we say that the model is trained on labeled data where input-output pairs are provided? Let's consider an example of supervised learning in the context of medical diagnosis, specifically predicting whether a patient has diabetes or not based on various health indicators. Imagine you have a dataset containing information about patients, including attributes such as their age, body mass index, blood pressure, insulin levels, and glucose concentration, along with a label indicating whether each patient has been diagnosed with diabetes or not. In this scenario, supervised learning can be used to train a classifier such as logistic regression or decision tree classifier to predict whether a new patient is likely to have this diabetes based on their health indicators. During the training phase, the algorithm learns patterns and relationship between the input features, which in this case are the indicators such as age, BMI, blood pressure, and etc., and the target variable, which is the output pair, which in this case is whether the patient has diabetes or not. It does this by adjusting its internal parameters to minimize the differences between its predictions and the actual labels in the training data. Once the classifier is trained, it can be used to make predictions on new patients. For example, if you have a new patient with unknown diabetes status but known health indicators, you can input their data into the trained classifier, and it will predict whether they are likely to have diabetes or not based on the patterns it learns during training. In this example, the labels indicating whether each patient has diabetes or not are provided by medical professionals as part of their training data. These labels serve as the ground truth for the algorithm to learn from. The goal of supervised learning in this context is to develop a model that can accurately predict the presence or absence of diabetes in new patients based on their health indicators, thus aiding in medical diagnosis and decision making. Now, moving on to unsupervised learning. In unsupervised learning, the model is trained on unlabeled data where the algorithm learns patterns and structures inherent in the data. Common algorithms would include k-means clustering, which is used for grouping similar data points into clusters such as market segmentation or anomaly detection, or hierarchical clustering, which divides data into nested clusters, providing insights into hierarchical relationships such as biological taxonomy or customer segmentation. Let's use the example of clustering items by color. When you apply a clustering algorithm to a dataset containing items with various colors, it will group them based on the similarities in color without any prior knowledge of what those colors represent. The algorithm simply looks at the features of the data, in this case, the color value, and tries to partition them into clusters where items within each cluster are more similar to each other than to those in other clusters. Once the clustering process is complete, it's up to the analyst to interpret the results. So in the context of our colored items example, after clustering, you might visually inspect each cluster and notice that one cluster contains mostly red items. At that point, you can decide to refer to that cluster as the red pile based on your own interpretation of the data. In essence, the names or labels assigned to clusters in unsupervised learning are typically determined by humans after examining the results rather than being intrinsic to the algorithm itself. So in this case, why would anyone ever use unsupervised learning rather than supervised learning, since the human still needs to do some work in unsupervised learning? Well, there's a lot of cases where you would have the data, you would have the features, you would have the indicators, but there are so many data points, and you do not have a ready set label that is assigned to each data point. So let's say you had 5,000 data points. A data analyst or whoever would have to go through every data point and label them. This would take time, money, resources, and is very prone to human errors. In this case, you could minimize the numbers from 5,000 data points to a few clusters, like 3 or 4 clusters. This makes it much simpler for the analyst, much faster, and there's much less chances of human error. Deep learning, as we mentioned, is a subset of machine learning that utilizes artificial neural networks with multiple layers to learn complex representations of data. Common architectures include convolutional neural networks, which is specialized for processing structured grid-like data, such as images or video frames used in image recognition, object detection, and autonomous driving. There's also recurrent neural networks, which is designed for sequential data such as time series or natural language employed in speech recognition, machine translation, and sentiment analysis. Deep learning models can be considered like the simplified versions of how our brains work. Both use interconnected units, in this case neurons, organized in layers, with information flowing through connections. Learning happens by adjusting these connections to get better results. They both process information in stages, starting with simple features and moving to more complex ones. While deep learning isn't as complex as the brain, studying it helps us understand how our brain might work. And vice versa, knowing some basic information of how the brain works also goes a long way in being able to build a deep learning model. Now, let's go over some use cases of machine learning. Machine learning is broadly used in finance. An example of that is algorithmic trading, predictive trading models for financial markets. Hedge funds and investment banks utilize machine learning algorithms to analyze market data, identify patterns, and execute trades automatically, achieving higher returns and reduced transaction costs. It can also be used to detect fraudulent transactions in banking and payment systems. Banks deploy machine learning models to monitor customer transaction in real time, identifying suspicious activities and preventing fraudulent behavior, safeguarding against financial losses. Machine learning is also used in retail. For example, in demand forecasting, it predicts product demand to optimize inventory levels. Retailers leverage historical sales data and external factors to train machine learning models, forecasting future demand accurately and minimizing stakeouts and excess inventory. It can also be used to adjust product prices in real time to maximize revenue and profitability. Online retailers use machine learning algorithms to analyze market demand and competitor pricing, optimizing pricing strategies dynamically to achieve higher margins and market competitiveness. It is the machine learning applications are growing more and more in medicine, as we have already seen. A common application for it is diagnostic assistance. AI systems exhibit high accuracy in illness detection, assisting healthcare professionals in diagnosis and treatment plan recommendations. These systems analyze medical imaging data such as X-rays, MRIs, and CT scans to detect abnormalities and assist healthcare professionals in diagnosing diseases like cancer, fractures, and neurological disorders. Now, on the other end of the spectrum, it can also be used for administrative automation. It can automate tasks like data input, claims processing, and appointment scheduling, which would save time and reduce human errors. By organizing patient records and processing insurance claims efficiently, AI streamlines administrative processes, reducing staff workload and improving overall operational efficiency. Now, the in machine learning applications is very, very widely used in marketing, as we have seen nowadays. A very popular example of that is content creation. AI-powered content generation platforms utilize machine learning algorithms to produce various types of content, including blog posts, social media updates, and video scripts. By leveraging AI for content creation, marketing teams can save significant time and resources that would otherwise be spent on brainstorming ideas and writing content manually. This allows for a faster content production process and ensures a consistent output of high-quality content tailored to the target audience's interests and performance. AI-driven audience analytics platforms can also analyze large datasets to segment audiences based on demographics, behaviors, and preferences. By accurately segmenting audiences, AI enhances targeting efforts by enabling marketers to deliver personalized messages and offers to specific customer segments. This increases the relevance of marketing communications, leading to higher engagement risks, improved conversion rates, and ultimately a more effective marketing strategy.